Okay, so in today's session, we are going to cover week 5 to week 8. Okay, so in week 5, we will start with what is rank of a matrix, right? So already we have seen how to do the Gaussian elimination. There is some echo. Is everything clear now?
Yes,
Yeah.
ma'am. It's
Okay.
clear now. Yeah.
Okay. So we have already seen how to apply Gaussian elimination to find the REF or RRAF form of a matrix, right? So now what is the rank of a matrix? So you take any m by n matrix A. The rank of the matrix A is the number of linearly independent columns of A. Okay. So this is a definition for rank of matrix, number of linearly independent columns of A. Okay, but this is not the only way to compute the rank. Okay, so we'll see. So the subspace spanned by the columns of A is called the column space, and the dimension of this column space is the column rank. Similarly, the subspace spanned by the rows of A is the row space of A, and the dimension is called the row rank. And it is we know that the rank, column rank, and row rank, everything is same, right? But usually what we do, we find the REF form and look at the number of non-zero rows in the REF form to find the rank of the matrix. This is the usual way to find the rank of the matrix. But in some cases, it is more easier by just checking the vectors. You can check the linear independence and also find the rank. That is also one way. Okay. So in for more complex matrices, this is a more reliable method. Find the REF form and look at the number of non-zero rows. That gives you the rank of the matrix. Okay, what is this is an important property for some problems. So if you have an m by n matrix, you know that rank of A is less than or equal to minimum of m comma n, right? So for example, if you have, maybe let us say you have a 5 by 7 matrix, what is the maximum rank of A?
5.
5, right? The minimum of 5 comma 7 is 5, so the maximum possible rank is 5. Okay, and the next property is rank of AB is less than or equal to minimum of rank of A and rank of B, right? So if one of the matrix has rank 0, then what can you say, or maybe say rank 1, what can you say about rank of A into B?
At most 1.
At most 1, right? Unless it is a 0 matrix, it will be at most 1, right? Okay, fine. So in the null space,
Ma'am, sorry to interrupt you. I just want little clarification, ma'am.
yeah,
Ma'am, we say that the rank of the matrix is a number of dependent variable, ma'am. In the
no,
first
no, no.
slide,
Dependent column. See, I have already warned you in the previous session, in the live session as well. Please don't confuse the number of linearly independent columns or rows with the independent variable concept. Independent variable concept is completely different from linearly independent rows or columns. Okay.
ma'am, can you little bit, ma'am, that clarify the relation because I remember, ma'am, the number of dependent variable is the rank of the matrix, and uh,
Is this what you are asking? So this one.
yeah, ma'am, yeah, ma'am, yeah, ma'am.
So
How
this
these
is
two are related,
variable.
ma'am? Yeah,
This is
ma'am, exactly.
variables.
Got it, ma'am. But I just want to know how these two are the same, ma'am. Just a little bit of clarification, ma'am. The
Okay.
number of the dependent variable and how the number of independent column are related and they correspond to the same rank of the matrix, ma'am.
So just consider this matrix. Okay. For this matrix, now what are the dependent variables first of all? Do you remember? Am I skipping something? Just one definition is there. Let me go with the flow so that I will answer your question as well. Okay.
Fine, ma'am. Fine.
Okay. So what is the null space of a matrix? If you take in an m by n matrix A, the subspace set of all x in Rn such that Ax is equal to 0 is the null space. We also don't know the null space as the solution space of the homogeneous system Ax is equal to 0, right? And we know that always this is a non-empty set because it contains the 0 vector, right? So the dimension of the null space is the nullity of the matrix A. Okay, so now look at this exercise. So here you have a matrix A and we are considering the homogeneous system Ax is equal to 0. Now what are the dependent and independent variables? So recall that for a matrix in reduced row echelon form, if the ith column has the leading entry of some row, we call xi a dependent variable And if the ith column does not have a leading entry of any row, we call xi to be an independent variable. Okay. So now here for this matrix, what is the RREF form? Can you tell? Or
1
REF
0
form?
0
Yeah.
0 0 1 0 0 0.
Okay. So now for this matrix, you can see that. So now the first column. So this is the first column. So the first column and the third column contain leading entries. So what can you say? X1 and X3 are
Dependent variables.
dependent variables, right? And X2 corresponds to independent variable. This is one part, right? On the other hand, see here, now look at the rows or maybe the columns. So now you see this is column 1, this is column 2, now this is column 3. How many linearly independent columns are there?
2.
Yeah. So C1 and C3 are the linearly independent columns. So you can see that according to the definition of rank, so rank of A is 2. Also, you can note that the number of dependent variable corresponds to the rank of the matrix. The dependent variable corresponds to the rank of the matrix. So this corresponds to the rank.
So
So you
can
should
we,
not, yeah.
sorry to interrupt, ma'am. So can we say that the columns which contain dependent variable is the linearly independent columns?
Corresponds to the linearly independent columns, because we are not looking at the matrix itself. When we are looking at the dependent variable, we are looking at the RREF form. So the corresponding columns you can say.
Okay.
Okay, so it is kind of not very clear, because sometimes we are doing column operations also, right? If you are doing column operations and doing column interchanging, then it is not very straightforward as to which column corresponds to the dependent variable from the original matrix compared to the RREF. But you can say that the number of columns corresponds to the dependent variables. You cannot exactly say that these are the columns which correspond to the linearly independent columns, because when performing RREF, it is possible that the columns are also shifting positions. Okay, so please don't stick to this. Just depend only for the numbers, not the columns.
Okay. If we are not doing the column operations, then it can be linearly independent columns as dependent variables column, right?
Yeah, yeah. Okay.
Ma'am, both of these definition, we get the result when the matrix is in REF form or RREF form.
See,
This
for
is
finding the linearly independent columns, you can either just observe the matrix and find, or you can rely on the RREF form also. It does not matter. But for finding the dependent variable and independent variable, you definitely need to look at the RREF form. Okay?
Thank you. Thank you.
Okay. Yeah. So now here, choose the correct statement from the following options. So already we have checked that x2 is the, this is not the correct option. This is not the correct option. So this option 3, x1 and x3 are the dependent variables and x2 is the only independent variable, right? So x1, so this is also incorrect. So this is the correct option. Okay. So now what is the null space and nullity of A? For this matrix, what is the null space? How do you find the null space? A very simple question here, right? So you can, you are talking about the nullity, but what is the null space? So you have the matrix 1 0 0 0 0 0 0 0 1, and then you have x1, x2, x3 equal to 0 0 0. So what is your null space?
0 1 0.
0 1 0, right? So your null space of A is the span of 0 1 0. This is because here you have x1 is equal to 0 and x3 is equal to 0, right? And only x2 is your independent variable, right? And hence you see that you can put this as 1. Okay, in fact, you can put any non-zero number, then the span of that vector is the null.
This applicable only to the independent variables. If there was a list of independent variables, if x1 and x3 are independent, then null space will be 1, 0, 1.
Yes. So it depends. See, if there are more, please mute yourself. So if there are more number of independent variables, then you will be getting more number of vectors accordingly. So only one independent variable is here. So only one vector is here. So suppose, for example, if your matrix is like this, suppose let us say it is 1 0 0 0 0 0 0 0 0. Now what will happen? Now for this you have
0, 1, 1.
x2 and x3 as the dependent variables, sorry, independent variables, right? So in this case, you will see that null space, let's call this matrix as B. So the null space of B is equal to span of, you have two vectors now, right? So only x1 is 0. So you have 0 1 0 and 0 0 1. You have two vectors now. Okay. So the number of independent variable corresponds to the number of vectors in the basis for the null space, right? Okay. And you can see that here the nullity is 1.
Yes, ma'am.
And here nullity is 2. Okay. Clear? Okay. So what is rank nullity theorem? Rank nullity theorem for an m by n matrix says that rank of A plus nullity of A is equal to n. Remember, here n represents the number of columns. Okay, n represents the number of columns. So now look at this matrix. Find out the value of A for which the matrix has nullity 1. So what is the way to do this?
Making one row as a linearly dependent.
Okay, that is one way. Yeah. So the other
Determinant should be 0.
Determine zero.
yeah. So if you are using this point which I mentioned here, use this technique. Rank of A is equal to n if and only if determinant of A is non-zero, or equivalently, here rank of A is strictly less than n if and only if determinant of A is equal to 0. Here, if this matrix has nullity 1, what should be the nullity of rank of A?
1.
Yeah. So it means rank of A is equal to 1 means determinant of A is equal to
0.
0.
0. So if you apply this property, A should be equal to
6.
6.
yeah. So you get A minus equal to 6 is equal to 0. So A is equal to 6. All right. Okay.
Ma'am,
Now-
sorry to interrupt. Can you repeat that question, ma'am? Just a little bit.
Okay. So here you have a matrix and you are asked to find a missing value, assuming that this matrix has nullity 1. Now, if this matrix has nullity 1, according to the rank nullity theorem, here n is 2, right? And you have 1 here. So from that, you know that rank of A is 1. So if rank of A is 1, you know that rank of A is strictly less than 2. So you know that determinant is 0. So now find the determinant, which is A minus 6, and equate it to 0. You will get A is equal to 6. Is it clear now?
Thank you, ma'am.
Okay. Okay. Let nullity of the matrix A be 2. Now you have a 3 by 4 matrix. Okay. So for a 3 by 4 matrix, can you tell what is the rank nullity theorem? So rank of A plus nullity of A should be equal to what for this 3 by 4 matrix? It's 4. Right? So now nullity is 2. So rank should be
2.
yeah. Okay, fine. Now look at the following question. Which of the following operations are correct for a square matrix A of order n by n, where n is any natural number? If the determinant is non-zero, you know that rank from here. If the determinant is non-zero, you know that rank is equal to n, right? So if rank is equal to n, then you know that the nullity must be 0, correct? So
Yes,
the
ma'am.
first option is correct. Is that clear? Why the first option is correct?
Yes, ma'am.
Okay. Okay. So what about the second option? Obviously incorrect. right? So it must be 0. So this is incorrect. What about the third option? If the nullity of A is non-zero, what does that mean? If the nullity of A is non-zero, it means that rank of A is
Less than n.
strictly less than n. So it means the determinant must be 0,
0.
right? So this again option 4 is incorrect. Okay, is this clear? This question?
Yes, ma'am.
Okay. Oh,
Ma'am,
yes,
excuse me.
yes, yes,
Okay, can you go to question number 2?
yes.
Okay, it is a 2 cross 2 matrix, so it is easy to find determinant.
Oh, yes.
Okay, if it is a rectangular matrix,
Okay.
and we have to find the value of A, like same question I'm telling you that that it has nullity 1 for find the value of A. If it is a 2 cross 3 or 3 cross 2 matrix, how to proceed? That was my
Okay,
doubt.
so in that case, what you can do is that you find the null space. Okay, so you know that the nullity is 1, so the spanning set should have only one vector. Okay, so from that you have to deduce. Okay, or you have to look at it. This is one way, or the other way is that, so suppose for example 2 cross 3 matrix or 3 cross 2 matrix or whatever it is, then you know what is the rank of the matrix. So from the rank of the matrix, you see what value of A can make two or one linearly independent column. The other should be dependent on the other. Okay, so for example, let us say you have 1, 2, 3A and then -5 and 10. Okay, -5 and maybe -10. Okay, you have something like this. Then
Okay, A should be 6 then.
yes, yes. Okay, so you can either look at the columns or rows to understand the value of A. Okay, fine.
Okay, thank you.
Yeah. Shall we now look at the problem number 5?
Yes,
So
ma'am.
if A is a 3/4 matrix, which of the following options are true? Rank of A must be less than or equal to 3. Is it true?
Less than or equal to 4.
Yes, ma'am.
Less than or equal to 4?
2, 2, 3.
3. You
Three,
forgot.
three.
It is minimum
Yeah.
of n.
Minimum of column.
Yeah, minimum of 3, 4, which is actually
Yeah, yeah.
3, right? So less than or equal to 3, right? Okay. Nullity of
Yes, ma'am.
A must be greater than or equal to 1. Is that correct?
Yeah, true.
Yes,
True.
ma'am. In this case, yes.
That is because what happens when rank of A is, so rank plus nullity, you know that it should be equal to 4, right? So rank can be either 3, 2, 1 or 0. So the corresponding nullities can be either 1, 2, 3 or 4. So it is always greater than or equal to 1 for this case. Okay. Oh, now if A has two columns which are non-zero and not multiples of each other, okay, while the remaining columns are linear combinations of these two columns, then nullity of A is equal to 2. First of all, from this information, can you tell me how many linearly independent columns are there in A?
2.
2.
2.
Two.
So it means that you have two linearly independent columns. So it means what should be the rank?
2.
Two.
So rank of A is 2. So if rank of A is 2, you know the nullity should be 2.
True.
So this is correct. And this is incorrect. Okay? Fine?
Yes, ma'am.
Now the next topic, linear transformation. You know that a function t from V to W, where V and W are vector spaces, is said to be a linear transformation if for any two vectors V1 and V2 and a scalar C, you know that TV1 plus V2 is equal to T of V1 plus T of V2 and T of CV1 equal to C times of TV1. Okay. So if these two conditions are satisfied by this function, then you know that it is called a linear transformation. What is one important property about a linear transformation? Always the zero vector is mapped to the zero vector. So this is the zero vector in V and this is the zero vector of W. Okay. Now look at this problem. Let T from R2 to R2 be a linear transformation such that T of 2, 1 is equal to 3, 2 and T of 1, 3 is equal to 0, 0. Which of the following option is true? Okay. So either you simply substitute T of 2, 1 and check whether you are getting 3, 2 or what is the usual way? Suppose let us say you are not given any of this option. How will you find t of x comma y? Okay, first of all, answer this question.
We
Does
express 2 comma 1 in terms of 1 comma 0 and 0 comma 1.
yeah. So does this set
Ma'am,
first of all make a basis for R2?
Yes, ma'am.
Okay. So first of all, this is a basis for R2. If this is the basis for R2 and you know the images of the basis element, you can find t of x comma y for any x comma y, right? So here I will give you the solution directly. So you know that if you take any x comma y and you want to write this x comma y as a linear combination of these two, I will skip the computation part and straight away give you the alpha and beta value. Alpha is 3x minus y by 5 and beta is equal to x minus 2y by 5. Now can you tell me what should be the next step? There is some
no,
minus
apply the
sign. Yeah.
transformation on both sides.
So yes. So now t of x comma y
Substitute
is equal to yeah.
Alpha into
So now you know that
3x minus
this is
3x
yeah
minus 5.
3x minus y by 5.
Ma'am, how this alpha and beta is calculated?
You have to solve the system of linear equation. What is the system of linear equation? You have 2 alpha plus beta is equal to x, and then you have alpha plus 3 beta is equal to y. You have to solve the system to obtain alpha and beta. Okay? Fine?
Okay.
So now t of 2 comma 1 is equal to here we are applying the linear transformation on both sides. Now you see that you have minus x minus 2y by 5 t of 1 comma 3. Okay. So now you apply the values here 3 comma 2 and 0 comma 0. So this part becomes 0. So only you have 3x minus y by 5 times of 3 comma 2.
3, 2.
So you will get what is the answer? 9x minus 3y by 5 and 6x minus 2y by 5. Right? So which is matching with this answer. Okay. So this is the usual procedure which I have specified here. So suppose,
Excuse me,
yes,
that above 3 alpha is equals to 3x minus 5 y by 5, what, how it came in?
that's what I'm saying. You have to solve the system of linear equation. Okay.
Okay, ma'am.
Ma'am, I have a doubt regarding transformation of 2 comma 1.
Okay.
As we have written it here as 3 comma 2.
Yes. T of 2 comma 1 is given as 3 comma 2. So that's why I have written as 3 comma 2. It's given to you.
Okay.
Okay.
Ma'am,
And this part is given as 0. Yeah.
ma'am, can we do one more thing in this case? Say, for example, because we know that, in this case, the t of x comma y we can take as ax plus by comma cx plus dy, right? It's in this format basically.
Yes.
So what we can do is that we already know two transformations, right? T2 comma 1 is 3 comma 2 and T1 comma 3 is 0 comma 0. Ma'am, we can
Yes.
solve for A, B and C, D and then also we can get the transformation, right? That is also one of the way we can do it.
Yes, you can do that as well. Yes.
Okay.
Okay.
Ma'am, please explain the third step, ma'am. It is
This one?
Yes, ma'am.
Okay, so let me show it here. See, what is happening here? You are having a transformation T from Rn to Rm. So in this case, it is from R2 to R2, right? And then you are having a set of basis vectors. So you are having some vectors. So if the domain is Rn, then you have n vectors, v1, v2, vn. Okay. Now you have to take a random vector from the domain. In our case, the random vector we have taken is x comma y. The next step is that you have to write the random vector as a linear combination of the given basis. Okay. So alpha 1 v1 plus alpha 2 v2 plus etc. alpha n vn. So here we have written alpha times of, so this is your v1 and v2. So I have written this random vector as a linear combination of v1 and v2. right? And then I have to solve the system of linear equation and find the coefficients alpha I. So alpha 1, alpha 2, alpha n. So here alpha and beta I am finding by solving the system of linear equation. Once I know what are these coefficients, the next step is that I apply t on both sides. So when I apply t on both sides, what I will get? T of v is equal to alpha 1 tv1 plus alpha 2 tv2 plus etc. alpha n tvn, right? So now here you see that exactly the same thing I have done. So t of x comma y is alpha times of t of 2 comma 1. Alpha is this value I have substituted plus beta times of t of 1 comma 3. Okay. So now the next step is that these values tv1 and tv2 are given to you. So you are substituting the values here. Okay. So this part is 3 comma 2 and other part is 0 comma 0, and then I'm simplifying. So the exact same thing you will do in the general scenario. You know what is tv1 tv2. Yes.
Ma'am, exactly problem happened is the calculated with 9x, where we calculated 9x, how this calculation is done, and the last part.
I'm just multiplying this with each of the coordinates. So 3 multiplied with this and 2 multiplied with this, that's all. 3 into 3, 9. 9 minus 9x minus 3y by 5, and then 6x minus 2y by 5. Okay.
Ma'am, while solving the system of linear equation 2 alpha plus beta equal to x. So
Yes.
what is the xy value, madam, over there?
That is what we are assuming as random values, right? So
Okay.
sorry. So what you usually do, the same process only. So you multiply 2 here to get this. Then you have first equation and second equation. Let's say, so this is first, this is second.
Okay,
So
okay,
now,
okay, got it.
okay, fine.
No, got it.
Okay. So this is the common procedure also. Now, what are the different types of linear transformation? It can be either injective, surjective, or bijective. Okay. So you say that monomorphism is other name for injective or one-to-one. So what is the definition? TV1 equal to TV2 implies V1 equal to V2, or TV equal to 0 implies V is equal to 0. The other way to say is that kernel of T is singleton 0, right? So the only vector in the kernel is singleton 0. Kernel is nothing but the null space of T, right? So all these are equivalent conditions for a one-to-one map. Now for onto or surjective map, what is the condition? For every element in the codomain, you have a pre-image. It means what? You have range of T is equal to W, or you can say rank of T is equal to dimension of W. Okay, so these are some equivalent conditions. And what about isomorphism? Isomorphism means both the conditions should be there, right? So if both the conditions are there, then you know that it is an isomorphism, both one-to-one and onto. In that case, for isomorphism, what will you get? You will get dimension of V is equal
to dimension of W.
W. Okay, fine. We define two vectors. Yes.
What is the difference between null space and kernel?
Null, see, they refer to the same thing. Only thing is that null space is quite often used for matrices and kernel is used for transformation, but both are referring to the same only. Okay, the terminology kernel is usually used for transformations. No difference. Fine. Any other questions?
Ma'am, rank of the transformation, as you mean, so the rank of the image, right? Basically.
See, rank of the corresponding matrix, you can say, or you can say dimension of the range space. Okay.
Okay.
Fine. Okay, so we define two vector spaces V and W as isomorphic to each other if and only if there exists an isomorphism T from V to W. Okay. So you can say two vector spaces are isomorphic if you have an isomorphic transformation from V to W. Just because two vector spaces are having same dimension, we cannot say that it is an isomorphism. Okay, it should be both one to one as well as on to. Okay, then only we can say that it is an isomorphism. Okay, so here are some things. So any n-dimensional vector space is isomorphic to Rn. Okay, and there exists an isomorphic linear transformation T from V to V if and only if the dimension of V is equal to dimension of W. Okay, now,
Ma'am,
okay, yes.
question. If it is other way around, just the dimension of V is equal to dimension of W, is it necessary that the linear transformation will exist between both of them?
There will exist a linear transformation definitely. That is why it is if and only if condition.
Okay.
Okay. So for example, let me ask a very simple question from matrices. So here you have, let us say you have W is equal to set of all A, B, C, D such that A plus B plus C plus D is equal to 0. First of all, is this a subspace? Can you quickly check, is this a subspace?
Yes.
Okay. This is a subspace. Okay. What is the dimension of this subspace?
3.
3.
So can you say to which space it is isomorphic to? It is isomorphic to
R3.
R3.
R3. Okay. Okay. So now let us say you have W1. Let us call W1 is equal to set of all x comma y comma z such that z is equal to 0 and x plus y is equal to 0. Can you say which space it is isomorphic to?
R1. R.
Which is just R. Right? Okay. Now let's say W2 is equal to set of all x comma y comma z such that x plus y plus 2z equal to 0. Now this is isomorphic to
R2.
R2. Okay. So you just have,
I really don't understand the conceptual part of it. Like how we are saying that it is a like a subspace, and why we are writing as R3, R and R2. I really don't understood the concept here.
okay. See here what we have done here, we have simply replacing, for example, you can replace any variable. Maybe I am taking D as minus A minus B minus C. So then you will have only 3 variables. This part I actually covered in the previous session, I guess, in the Endterm session as well as in the live session. So if you have attended, you know that this space has dimension 3 and you can find a basis consisting of 3 vectors. So if this is having dimension 3, then it is isomorphic to R3. And here this space is having, so this dimension of W is 3 and hence isomorphic to R3. Here dimension of W1 is 1 and hence isomorphic to R1. And here dimension of W2 is equal to 2 and hence isomorphic to R2. Okay. So if you have definitely seen the previous session, you would have understood this already.
Yes, I understood when you when we have just a little information.
Okay, fine, good.
Ma'am, sorry to interrupt you, ma'am. Just ma'am, little recapitulation. Basically, I remember I just forgot one thing. Ma'am, for WI, it's clear, ma'am, that dimension of W is equal to the dimension of V, which is R3, ma'am. So they are isomorphic. In second case, ma'am, can you little bit explain, ma'am?
See, in the second case, what's happening is that Z is 0. So the third coordinate is 0. So you have X and Y is minus X. So only one variable is here. So you can take this X commonly and then you have 1 minus 1 0 and this will form a basis for this space.
Okay, ma'am. And ma'am, W2, ma'am?
W2, see, what is the equation AX plus BY plus CZ equal to 0 representing? This always represents a plane
Yeah, ma'am.
passing through origin in R2. Sorry, in R3. Okay, so this means that it has dimension 2. Always for any plane passing through the origin, the dimension is 2. Okay.
Thank you, ma'am. Thank you.
Yeah.
Ma'am, in the question R3, R1, and R2 will be given, ma'am.
See, I cannot tell how the question is going to be. From whatever I have explained here, you will be able to, if you have understood it, you will be able to answer.
Ma'am, in this explanation, ma'am, I refer, ma'am, the R3,
See, for
R1.
example, there is one more thing can happen. For example, let us say, maybe let me give some more things. Let us say you have the xy plane. Let's say this is your v1. Okay, so let me say v2 is the set of all x comma y such that x is equal to y. Okay, and then your v3 is set of all A, B, C, the diagonal matrices in 3 by 3 diagonal matrices. Okay. Now, can you match the isomorphic spaces? So you have these spaces on one side and these spaces on the other side. So can you match W? Which space will you match for W? For W, what is the matching space?
V3.
V3, because here the dimension, you have 3 elements, so the dimension is 3. What about W1?
V2.
V2, because here the dimension is 1, right? It is a straight line passing through origin in R2. So for any straight line passing through origin in R2, you know the dimension is 1. And what about W2? Only one option is left anyway. So it is V1. So this is also a plane passing through origin, right? The XY plane, it is a plane passing through origin. So the dimension is 2. Okay. So
If
either
two-dimensional things are given, ma'am, so they are isomorphic. If dimensions of particular one vector and the other vector's dimensions are same, then they are isomorphic or not?
yes, two vector spaces of same dimensions are isomorphic. Okay. That is what this note 2 tells you. If two vector spaces are having same dimension, then they are isomorphic. Okay.
There exists a isomorphic, but there is a
See, what is the definition of isomorphism? If there exists an isomorphism T from V to W, right? Two spaces are said to be isomorphic if and only if there exists an isomorphism. Here, there exists an isomorphism from V to W, so that it means that V and W are isomorphic, right? Okay.
Yes, ma'am.
That is the definition. Got it?
Yes, ma'am.
Ma'am, in that way, ma'am, we assume that the transformation exists between B and W, ma'am.
If the dimensions are same, yes. We are not assuming, it will exist.
Okay, ma'am.
Ma'am, let's move further.
Yes. So moving to week 6. So as I told you, kernel or null space of T refers to the set of all vectors in V such that TV is equal to 0. This is a vector subspace. And image or range space of a linear transformation T is a set of all vectors in W such that TV equal to V for some V in V. Okay, so the set of all vectors in the codomain which has a pre-image in the domain. Okay, so the dimension of the kernel is called the nullity and the dimension of the range space is called the rank. Okay, so what is the relation between injective map and nullity? So if T is injective, you know that nullity is 0 because kernel is 0, right? And if T is surjective, that is onto, then rank of T is equal to dimension of W. And when T is bijective, that is isomorphic, then you know that rank of T is dimension of W, nullity is 0, and hence from rank nullity theorem, dimension of V is equal to dimension of W. Okay. So,
A little bit about, ma'am, the third relation that was talking about bijective map, rank, and nullity. I
yes.
really want some information.
See, what is the rank nullity theorem telling you? Please mute. Rank of T plus nullity of T is equal to dimension of V. This is the rank nullity theorem for a linear transformation. Now, If it is bijective, rank of T equal to dimension of W. So this part becomes dimension of W and this part is 0. So you will end up with dimension of W equal to dimension of V. Okay, fine.
Okay.
There is a question. So relation between subjective map and the rank. For example,
Yes.
I'll give you the example for R3 to R2. My R3 having a matrix full rank matrix. So it is 3 into 3 matrix. But it is
Hold on.
mapping to R.
What is the matrix size?
It's a 3 into 3 matrix.
But you said the transformation is from R3 to R2. Then the matrix size should be
2 cross 3.
2 cross 3.
So what is the maximum rank?
2.
Okay,
if you are
ma'am.
saying
Got
full
it,
rank,
got it.
Nullity is 1.
Okay. Okay. Moving on to this question. T
Got
is
it.
a
Thank you.
one-to-one. Yeah, okay. T is a one-to-one linear transformation if and only if there does not exist any V non-zero such that TV equal to 0. See, if T is one-to-one, what do we know? Kernel is
0.
Singleton
0.
empty set.
So it means what? It does not contain any non-zero vector, right?
Yes.
So this option is correct. Okay. So if T from R2 to R2 is surjective, then it cannot be injective. Is that true? No, right?
It
So
can be bijective.
several examples, right? What about T of x comma y equal to x comma y itself, the identity transformation? It is surjective and also injective, right? Definitely there are isomorphic transformations from R2 to R2, right? Yeah, you
The
can give
simply
plenty of
statement is also speaking, na, ma'am. Simply
Sorry?
speaking, the statements of surjectives or like already speaking like that cannot be injective, na?
No, see, if it is surjective, why it cannot be injective? Because what is the statement first of all saying? If T is from R2 to R2, then you first of all know that R2 to R2 there exists a isomorphism, right? If there exists an isomorphism, then for that mapping, at least you know that it is injective, right? Yes or no?
Yes, yes, ma'am. Yes, yes, yes.
Okay. So this is true. Okay. What about option 3? If T from R2 to R is a linear transformation and it is not injective.
Says it cannot be, ma'am. The statement says it cannot be. It can be, na? The statement should be not true, na?
Yes, it's not true. Yeah. So if T from R to R is a linear transformation which is not injective, then T must be 0. Okay. So what does this mean? If it is not injective, the kernel contains a non-zero element. Okay.
Yes.
Not injective. So kernel contains a non-zero element. Okay. So it means what T is from R to R. What is the general form of a linear transformation from R to R? T of V will look like, or T of U, let us say, T of U should look like alpha U, right? This is the general form for T from R to R, right? Now it is given that you have a vector in the kernel which is non-zero. It means what? You have TU or TV equal to alpha V, TV equal to alpha times of V equal to 0. So this means here V is non-zero. So this implies alpha equal to 0. So your T of U is equal to 0. So this means your T is a 0 transformation, correct? Yes,
Yes.
or no? So you know that TV equal to 0 for all V in R. Clear? Okay.
Yes, ma'am.
What about option 4? If there exists some non-zero vector such that TV equal to 0 for a linear transformation T from V to V, then T cannot be isomorphism. So it means, first of all, what they are saying, the kernel contains a non-zero element, right? Then this means that T is not 1-to-1. If T is not 1-to-1, then T cannot be an isomorphism. So this statement is also true. Clear?
Ma'am, in option number 3,
Yes.
For all non-zero vectors which are present, has to be mapped to 0. That's what it's
Yes.
trying to say.
Yes. Yes. Okay. Fine. So moving on to matrix representation of a linear transformation. So how do you do a matrix representation? Suppose you have a linear transformation T from V to W. Okay. Then you have some basis for the domain and some basis for the codomain. What you first do, you first of all look at what are the transformations for the basis elements of the domain. Then what you do, you write each of these transformed vectors as a linear combination of the basis elements of the codomain. Okay. Now what you do, you take these coefficients of V1, V2 up to Vn, put them as columns of a matrix that gives you the matrix representation of T with respect to beta and gamma. Right? So here look at this example, T from R3 to R2, and this is the transformation. Now choose the correct option about T. Okay, so the matrix of T with respect to the standard basis. What is the matrix with respect to the standard basis for both R3 and R2? So what is T of 1, 0, 0?
0.
2, 0. And what is T of 0, 1, 0?
1, 0.
1, 0.
And T of 0, 0, 1?
0, 1.
So this is your V1, V2, V3. So we write TV1, TV2, TV3 as columns. 2, 0, 1, 0, 0, 1. So which option is correct?
Second.
Yeah. So this is incorrect. Right? Now a basis for the null space of T is, what is the basis for null space? We have to find. So this is the matrix you have. Now what is the null space? Either you can look at the transformation straight away. So you can look at the transformation, how to find the null space from the transformation. So you have to assume T of x comma y comma z equal to 0, which means 2x plus y comma z is equal to 0 comma 0, which means 2x plus y is equal to 0 and z is equal to 0. So it means what? You will get y is equal to minus x minus 2x. Right? Y is equal to minus 2x. So your null space is given by set of all x comma minus 2x comma 0. X in R. So what is the basis you can see? X times of
1, minus 2, 0.
1 minus 2 and 0.
Minus 0.
X times of 1 comma minus 2 comma 0 in R. So you see that this is a basis. Right? So this is the correct option. You cannot have two elements in the basis because the null space nullity is 1. So this is incorrect. And what about the range? In the range, you see the columns. For range, you look at the columns. Now in the column, how many linearly independent columns you see?
2.
2. So you can either take this or this, and then you can take the other one. So they have picked 2, 1 and 0, 1. So is this a basis for this? How can you verify that this is a basis? Will you be able to obtain 1, 0 or 2, 0 from this?
Yes.
Yes, right. So let us call this as U1, U2. So you know that you will be able to obtain this column. So which is U1 minus U2. You will get the first column. And then this is your already existing column. So you are obtaining these two spanning columns from this. So this also forms a basis. Clear?
Yes.
So the rank is 2. So you cannot have a basis consisting of one element.
Ma'am, sorry to interrupt you, ma'am. Can you just recapitulate, ma'am, option number 5, ma'am, once again?
See, in option number 1, you are given 2 vectors and you are asked to
It's
check
a 5, option 5, ma'am.
Yes, option 5 only I am talking. You are given 2 vectors and you are asked to check whether it forms a basis for the range. Okay, So now what is it you can see? You have two linearly independent columns in the matrix A. So what are the linearly independent columns? So either you can take 2, 0, 0, 1, or you can take 1, 0, 0, 1. Okay, it is our wish only. So these are the linearly independent columns. Now you have to check whether you will be able to get these two vectors from these two vectors given here. You can, let us call this as u1 and u2. You can note that this is u1 minus u2. So you are able to get the first vector from this set. Same way, the second vector is simply u2. So you can see that both these vectors are obtained from here. And these two linearly independent vectors, we already know that this forms the basis for the range of T. Right? So if you are able to obtain these basis vectors from this, then this will also form a basis. Okay?
Got it, ma'am. Ma'am, I just forgotten because quiz 2 is long back, ma'am. Ma'am, just general way, ma'am, I just want to recapitulate. If you find the range of the T, how will we proceed, ma'am? For example, I don't have to verify. I just want to get the basis for the range of the T, ma'am. Just can you elaborate, ma'am? Will be thankful.
See, you just have to pick the linearly independent columns that is sufficient to find the basis for range of T. Pick the linearly independent columns of the matrix. Okay?
Okay, ma'am.
Okay. So this is a problem which just summarizes the properties. Suppose you have a transformation T from R3 to R3 and the general form is given here. And you have a matrix representation given here. So T is injective if and only if the system of linear equation has a unique solution. Is that correct? Yeah, this is the definition, right? In fact, so if this AV is equal to 0 has a unique solution, this means the null of A is equal to 0. So it means your kernel T is 0. So the transformation is 1, 1. Right? Okay. And T is injective. So nullity is 0. If nullity is 0, then rank must be 3. Right? And the other thing is that if the system of linear equation AV equal to B has a solution for all B, it means what? TV is equal to B has a solution for all B in R3. It means every element in R3 is having a pre-image. So every element in R3 is there in the range. So it means your range is entire R3 and hence T is surjective. Is it clear? The third option?
Yes, ma'am.
And the fourth option says that T is not surjective. It means at least one for one B, AB equal to B has no solution. Okay. So everything is just from the definition. These are, see, this, if you know, you are almost able to answer most of the questions related to injective and surjective. Either it is in the matrix form or in the transformation. If you have an understanding of these points, you will be able to answer most of the questions from this topic. So please try to understand all these options here.
Ma'am, can you please repeat option 3 alone once again? Option 3, why it is 2?
See, what is the definition of surjective? Surjective means that every element in codomain has a pre-image.
Yes.
Right? This is the definition of surjective. Now, for what is given here, if the system AV equal to B for any B in R3 has a solution. So let us rewrite the same equation in terms of the transformation. So you have TV equal to B. Now for any B in R3 means, for any B in R3, it means that for every element of codomain. Okay, the pre-image is the solution of TV equal to B. And you see that it has a solution, so it means that you have a pre-image. The solution is your pre-image. Got it?
Okay.
Ma'am, from option 3, can we conclude that the matrix, the transformation matrix is isomorphic?
No. Here only we are talking about surjective. We are not talking about injective. But anyway, since the transformation is from R3 to R3, then you know that it is onto one-to-one also. I don't know whether I have stated this result somewhere else, but anyway, I will point it out because it is an important result. Let us say you have T from V to W, and dimension of V is equal to dimension of W. Suppose this is given to you. Then T is 1-to-1 if and only if T is onto. It means what? Suppose you have a transformation where the domain and codomain are having the same dimension, then 1-to-1 implies onto and onto implies 1-to-1. So here T is from R3 to R3 and you have surjective, then you should also have injective. Okay?
Okay. Yes, ma'am.
Okay. So quickly, can you check whether this is 1-to-1 and onto?
Ma'am, sorry to interrupt you, ma'am. Just confirmation, ma'am. If we have, ma'am, dimension of W is equal to dimension of V, and we have any of the one is it's either 1 or 1, or then we can interfere. It's also onto. If it's
Yes.
onto, we can interfere. It's 1, 1, 1, and 1.
Yes, yes.
Okay.
So quickly, can you tell whether it is 1-to-1 and onto?
This is 1-1.
It is 1-to-1, right? Because here what, suppose you have T of x comma y is equal to x comma 0, then what you get? You will get that T of x comma, and this is equal to 0 comma 0. Let me see your answer is correct or not. So you have 0 comma 0. Now what does this say? It tells x is equal to 0. Now what is the image of T of 0 comma 1?
0, 0.
0, 0. So it means that 0 comma 1 belongs to kernel of T. Now tell me, is T 1-to-1?
No.
So T is not 1-to-1. So now without computation, can you tell me whether T is onto?
No, ma'am.
Because just now we saw if it is 1-to-1, then it is onto, right? So, and if it is onto, then it should be 1-to-1, right? So equivalently, you can say that T is not 1-1 if and only if T is not onto.
For this dimension of V, only in this case when dimension of V and dimension of W is same, right?
Yeah.
Got it.
So it cannot be onto as well. Okay. What about this one? See, there is another way. See, here you have used the definition. What is the another way to check 1-to-1 or onto? Can we use matrices?
Yes,
So what is the
we can
matrix
use
representation for this? What is T of 0, 1, 0? 1, 1,
1,
and 0, 1 is?
1, minus 1.
So the matrix is 1, 1, 1 minus 1, right? So this is TV1, TV2. So V1, V2. Okay. So now, what is the determinant of this matrix? Or you can
minus 2.
Determinant is minus 2 and non-zero.
Full
Right?
rank matrix.
Yes. Rank of A is 2. So if rank of A is 2, you know that T is onto.
Not 1, 1.
So you know it is 1, 1 as well.
Correct.
Yeah.
Okay. So you can use matrices also to conclude 1-to-1 and onto. Okay.
So here you have taken T of 1, 0 and 0, 1 basis of R2, right, ma'am? Standard basis, right?
Yes. Okay. So here we have the matrix representation of T. This is very easy. What is the appropriate definition of T? So T of x comma y is nothing but A times of x comma y. So simply you have to multiply 2, 3, 1, 4 with xy. What's the answer?
4. Option 4.
2x plus 3y, x plus 4y. This one. Right? Okay. So is this T 1-to-1 or onto? What is the determinant of A?
Both 1, 1 and
Both 1, 1 and onto.
Yeah, determinant is non-zero.
Non-zero.
So it is 1-to-1 and onto. Okay. Now what is the matrix?
Ma'am,
Yes.
Ma'am, I didn't get what exactly we have done over here. We are saying T of xy is equal to A of xi. I didn't get what is this.
See, if you are given a transformation, you know how to find the matrix.
Yes, ma'am.
Now, if you are given a matrix, this is how you find the corresponding transformation. Particularly here, it is
Okay.
the
Yes, ma'am.
standard basis for both domain and codomain. So straight away you can find the transformation in this way.
Okay, using the matrix.
Yes.
Okay.
Okay. And what will be the matrix representation of with respect to the basis beta for W and gamma for R2? What is beta here, by the way? Is some data missing? Beta is the standard basis, maybe. Is that so? Let me just check. So, yeah, beta
If the
is.
base is not given, then we should consider a standard basis. No?
Yeah, so let's take the standard basis as beta. Okay, now we already know what is TE1. Can you tell what is TE1 without calculation? Just by looking at the question, can you tell what is TE1? That is T of 1, 0. Can you quickly tell?
2, 1.
2, 1. The first column represents T of 1, 0, right? 2, 1. And what is T of 0, 1?
3, 4.
3, 4. Now T of 1, 0, you have to express as 1, 1.
Plus.
Linear combination of 1, 1 and 1 minus 1. So alpha times of 1, 1 plus beta times of 1 minus 1. So let's maybe call alpha 1, beta 1. So that you have alpha 2, 1, 1 plus beta 2, 1 minus 1. So what are the coefficients alpha 1 and alpha 2? How will you find?
Alpha plus beta equal to 2.
Yes, you have to solve alpha 1 plus beta 1 is equal to 2 and alpha 1 minus beta 1 is equal to 1. You have to solve this. So if you solve this, what will you get? 2 alpha 1
is equal to 3 by 2.
Alpha 1 equal to 3 by 2. So from this you can compute beta 1. Same way you compute alpha 2 and beta 2. So I will give this as a homework. Complete finding alpha 2, beta 2 and beta, what is missing? Beta 1. Okay. So what is the required matrix here? The required matrix is alpha 1, beta 1, alpha 2, beta 2. Don't forget the order. Alpha 1, beta 1 should be the first column. Alpha 2, beta 2 should be the second column. Okay. Fine. Now consider the linear transformation T from R3 to R2 defined by this transformation here. What is the null space? How will you find the null space?
Equate to 0.
Yes.
P is equal to 0 plus B
Right. So if you equate to 0, you get 2x plus y equal 2x plus 3y equal to 0 or 3z, right?
Yes.
3z equal to 0 and then you have 4y plus z is equal to 0. Okay, so now what we can do, you have z common in both the places, so maybe you can fix z in both the scenarios. So z is equal to minus 2 by 3 x and here z is equal to minus 4y. So what you can have is null of t is given by set of all x comma, or instead of z you have, okay, maybe I should have x in terms of z and y in terms of z. That is what makes sense, not like this. So here you have x is equal to
Minus 3 by 2.
minus 3 by 2z and y is equal to minus 1 by 4z. So you will have minus 3 by 2z comma minus 1 by 4z comma z in R. So the basis you can see is minus 3 by 2 minus 1 by 4 comma 1, or if you want them to be integers, you can simply multiply it with 4 and get it. Okay, so if you multiply it 4, you will have minus 12, right, or minus 6 here, and then here minus 1 and 1.
4, no?
4.
Yeah? Is it
4.
fine?
Minus 6, minus 1, 4.
I'm multiplying with 4.
Last term is 4, ma'am.
Yeah, it's 4. Okay, so now this is a basis for the null space of T. Okay, and what will be the dimension of the subspace image of T? You already know the null space has dimension 1. According to rank-nullity theorem, when you apply it here, rank of T is equal to 2 minus nullity of T. So 2 minus 1, 1. So the rank should be 1. Is it fine?
Can you explain this part again, ma'am?
See, what is rank-nullity theorem? Rank-nullity theorem tells you that rank plus nullity is equal to rank of T plus nullity of T is equal to dimension of, sorry, here I made a mistake. It should be dimension of domain.
Yeah, it should be 3, right, ma'am?
Yeah.
That's
so it is dimension of domain.
Correct. 3 minus 6. Correct. Yeah.
So here it is 3. So 3 minus 1, 2. So the answer is 2.
Now I got it. Yes.
Okay, fine.
So how we are equating to 0, ma'am, here, linear transformation?
Because we are finding the null space. What is the definition of null space? Set of all x such that tx is equal to 0, right?
Yes.
So that's why I am equating tx is equal to 0. So t of x comma y comma z equal to 0. If I want to find what are all the x satisfying this condition, this is what I need to do, right?
Okay. Thank you.
Okay. Now can you choose the correct option? Can T be an isomorphism?
No.
It cannot be an isomorphism.
Dimension
What about 1 to 1? It is it 1 to 1? It has a non-zero element.
Yeah,
No.
it cannot be.
It cannot. Is it on to?
Yeah, onto.
Yes, because the dimension of the image is 2 and
2,
the codomain
the
is
rank.
R. So this is 1 to on to, but not 1 to 1.
Ma'am, can you repeat please now once?
See, here the dimension of the subspace image of T is 2, right? So it means you have rank of T equal to dimension of codomain R2. So it means what? It is surjective. T is surjective.
Yes, ma'am.
Right? So T is on to, but not 1 to 1. Is this clear? This problem?
Okay, ma'am. We are matching the dimension of the image with respect to dimension of the codomain, right?
Yes, for on to, that is what we need to
So
check.
it's 2, 2, 2. So that's why it's on to.
Yes.
Okay.
Fine. So here T from R2 to Rn to Rn be a linear transformation. Note that this is something very important. T cannot be onto if m is greater than n. Okay, so if your m is greater than n, then T cannot be onto. What happens when T is onto? Then rank of T is equal to m, but this will contradict your rank nullity theorem, right? For rank of T, the maximum value is n only, right? But here m is a value greater than n, so it is not possible. Same way, T cannot be 1 to 1 if m is less than n. Why? If m is less than n, what happens when T is 1 to 1? Nullity is 0, implying rank of T is equal to n. But rank of T is less than or equal to m, and n is a value bigger than m. So this is also not possible. So these are some scenarios from which you can tell the answer without even computations. So for example, you take T from R2 to R3. Can this be on to?
Not possible.
No.
Not possible. Same way, the other way around. T from R4 to R3. Can this be 1 to 1?
No.
No.
It cannot be. Okay, fine. Okay, so look at this problem. Consider a linear transformation T from R3 to R3 defined in this way, such that ABC is not equal to 1. Which of the following options are true? So the matrix representation of T with respect to the standard basis, first of all, what is the matrix representation? What is T of 1, 0, 0? 1 minus B
Minus 1 minus B
0.
0.
T of 0, 1, 0 is A, 0, 1. And T of 0, 0, 1 is 0, 1,
0, 1, C.
C. Right? So 1 minus B 0, A 0, 1, 0, 1, C.
When T
So
of
this,
when T of 0, 1, 0 is A 0. Okay, okay, fine. Got it.
okay. So you see option 2 is correct. And what is the rank of this matrix? What is the determinant of this matrix? Can you quickly compute the determinant? Let's call this A. Find the determinant of A. 1 times of, you have minus 1, and then minus A times of minus BC. So which is minus 1 plus ABC. And it is given that ABC is not equal to 1. So it means this is not equal to 0. So if the determinant is non-zero, what do you know about the rank of the matrix?
Full rank.
Full rank.
So rank of A is equal to 3 implies that image of T is equal to R3,
0.
right?
R3.
Right? So if your range is equal to entire R3, so the basis for the range is 1, 0, 0, 0, 1, 0, 0, 1, 1. Here there is a mistake, 0, 0, 1. Okay? So this is a correct option. This is incorrect. This is also incorrect because rank is 3 for us. And rank is 3, you know that nullity is 0. Clear?
Ma'am, one small doubt. Whenever we are creating matrix from the linear transformation, it should be in column wise, right? The vector should be represented as column wise.
Yes.
Okay.
Okay. So now in week 7, for equivalences of matrices, so two matrices we say equivalent. So if you have this condition, B is equal to QAP, where Q and P are invertible matrices. You know that this satisfies an equivalence relation, right? And what is a special case you have? How, see, in all the scenarios, finding P and Q is not that easy, but in this following scenario, what is that scenario? When you have a linear transformation T from B to W. Please mute. I'm going to mute all. Yeah. Okay. So you have a transformation T from V to W, and you have a basis beta 1 and beta 2 for V and gamma 1 and gamma 2 for W. Now you have a matrix representation A with respect to beta 1 and gamma 1, and you have a matrix representation B with respect to beta 2 and gamma 2. Now you know that A and B are equivalent. When you have these two types of matrices under this kind of a condition, they are equivalent, and you have this condition B equal to QAP, where specifically your P is nothing but the expression you have to express your ordered basis beta 2 in terms of beta 1. Okay, and the coefficients gives you P. And similarly, you have to express gamma 1 in terms of gamma 2 to get the coefficients Q. Okay, so this is some time consuming procedure, but anyway, finding P and Q is much simpler than a random scenario. Okay, in this case, you at least have a procedure to find P and Q. Okay, so these are very important conditions.
Could you explain a bit?
Please refer to the live session video for more explanation, because it is going to take time, and here in the revision session is not the place for complete explanation of the concept. Okay.
So just a simple word of P, B, P, and Q.
That is what I told you. The simple word is P is expressed is the expression of the ordered basis beta 2 in terms of beta 1. So this is your beta 2, and you are expressing it as a linear combination of the elements of beta 1. And these coefficients, you are writing them as columns and finding P. Same way for Q, you have to express the ordered basis gamma 1. So W1, W2, Wm are the ordered basis gamma 1 that you are expressing as a linear combination of gamma 2, which is x1, x2, xm. Now each of these coefficients, you are writing them as columns and finding Q. Okay. Right. So now other characterizations are two matrices are equivalent if A can be transformed into B by a combination of elementary row and column operation. Okay. So if you are able to transform a matrix A into B by a series of elementary row or column operation, then those two matrices are equivalent. Okay. But the more general thing to do is that to check their ranks. If two matrices are having same ranks, then they are equivalent. But remember, if they are of different order or different sizes, then definitely you don't have to check anything. Straight away you can say they are not equivalent, because equivalent matrices we talk only for matrices of same size. So for example,
Ma'am, rank of A is equal to B is the main check for equivalency, no?
no, for example, let us say you have this matrix. Okay, what is the rank of this matrix?
Minus
What?
2.
1 minus E.
Rank is 2 for this matrix.
Oh, yeah, sorry. That is
Now
right.
look at this matrix. What is the rank?
2.
But they are not equivalent. They are of different size. Okay, they are not equivalent. They are of different sizes. Different sizes, you do not compare them for equivalence at all. Okay, even the ranks are same, it does not matter. Different sizes, you don't check for equivalence at all. Okay, so here
If the similar matrices are given, ma'am.
Sorry?
If 2 cross 2 of two matrices are given, then?
If the same sizes are given, then you can apply this condition that they are equivalent if rank of A equal to rank of B. Okay, so you can clearly see that two matrices are equivalent because both of them are having the same size and same rank. Okay, both are of same size and same rank, so they are equivalent. Okay.
Ma'am, for the rank, do we need to have the REF, or like straight away we can see the matrix and then see the 0 and we can tell that?
Rank you can find in whatever method you know. There is no fixed way. Whatever method you know, you can apply to find the rank. Okay, unless you have a specified question where the options involve some specific technique, then only you have to go to the technique. Otherwise, you can follow any method you know. Okay. Here some confusion has happened while editing, so don't worry. Okay, so similar matrices. What are similar matrices? Similar matrices are two matrices if they are, first of all, equivalent matrices are for rectangular matrix, while similar matrices are only for square matrices. So you have n by n matrices, and you say that two matrices are similar, okay, if B is equal to P inverse AP, where P is an invertible matrix. Okay, so note that similarity is only applicable for square matrices. Okay, obviously similarity implies equivalence, but the other way is not true, right? For example, take these two matrices. Are they equivalent?
Yes.
Both of
Yes,
them are having
rank are 2.
Yeah, rank of A equal to rank of B equal to 2. So A and B are equivalent. But are they similar?
No.
No, because B is equal to P inverse AP will give you here A is your identity matrix, right? So P inverse IP is simply identity. So B is equal to I, but this is not true because B is not equal to identity, right? So A and B cannot be similar, but A and B are equivalent, but A and B are not similar. So you cannot have the other implication that one way you know A and B are similar implies equivalence, but equivalence do not imply similarity. Okay, so the exact same procedure we have.
When we are saying equivalence QAP and for similarity P inverse AP, both are different, right? It doesn't mean same matrix should be invertible. That's what we are checking in similarity.
Sorry, what?
In equivalence, we are saying QAP, right?
Yes.
So Q and P should be invertible, right?
Yes.
And here we are saying P inverse AP.
Yes.
Here that is also invertibility, right?
Because here invertibility is like automatically we are able to see it. Only when P is invertible, P inverse makes sense, right?
So same matrix we are considering here in similarity. There
Yes.
Q and P are different matrices, right?
Yes, yes.
Okay.
Okay, and for similarity, the similar situation here we have, only thing is that here you are going to have the same space for domain and codomain. So for a transformation from same domain with to the same codomain, okay. So you see that suppose you are having two different bases and you have a matrix which has the same basis for the domain and codomain. Same way B is having the same basis for the domain and codomain. Then A and B are similar and you can find P in the following way, which is similar to the previous method we have seen. Okay, fine. What are the properties of similar matrices? If two matrices are similar, they have same rank, same trace and same determinant. Okay, these are properties, but these are not equivalent conditions of similarity. Remember that, because here for these two matrices we already saw that they are not similar, but they have same rank, same trace and same determinant. You can easily see that the rank of both the matrices are 2, the trace of both the matrices are 2 and the determinant of both the matrices are 1, right? But you see that they are not similar, that we have already seen. So the converse of the above statement is not true. Okay. Now let's try to answer this question. Let A be an n by n matrix which represents an isomorphism between two n-dimensional subspaces. Okay. Can A be similar to matrix B whose nullity is greater than or equal to 1? A is representing an isomorphism. If it is representing an isomorphism,
No. False.
okay, first of all, what should
Nullity
be
is
the rank
0.
of, yeah, what should be the rank of A?
Full rank matrix.
It's n.
N, right? If rank of A is equal to n, you know that nullity of
Nullity is 0.
A is 0, right? First of all, if rank of A equal to n, what should be the rank of B? A and B are similar.
Same. N.
Same rank.
So they should have the same rank. So you know that nullity of B is also 0. So it cannot be greater than or equal to 1. So the answer is no. Okay, fine. Which of the following options are true? If A and B are similar, then A inverse and B inverse are similar matrices. True or not?
True.
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 This you can easily verify, right? So B is equal to P inverse AP. Just take the inverses. Then you will get that B inverse is equal to PA inverse P inverse. Right? So P inverse, or you are getting the same. P inverse, A inverse, P only.
Ma'am, the inverse should exist for that to be true, no?
Yes. If you are saying that A inverse and B inverse are similar, we are kind of assuming that A inverse and B inverse exist, then only this statement is made. Okay, fine. If A and B are, yes.
In the previous one, there will be question for a domain and codomain for a beta and gamma same, so it's basic. That could you explain it again? Yeah, this one.
Okay, which part you want me to explain?
This is whole I don't understand about the A and B. So matrix representation from beta from W, V to W. I don't understand. Could you explain?
See, T is the so A is the matrix representation of T, where the basis you are considering for the domain and codomain both are beta. So, for example, suppose you are considering 1, 0, 0, 1 for both domain and codomain. Okay, then you say that that matrix is A. For example, I'm saying, okay, and let's call this as beta. And let's say you have another gamma. So gamma is, let's say, 1, 1 and 1, minus 1. Okay. Now your B is T of gamma. So it means what? You are first of all finding t of 1, 1 and expressing it as a linear combination of these two. And again, you are finding t of 1, -1 and expressing them as a linear combination of these two. Then you are finding b. Now a and b are similar. Okay.
So this is a linear transformation, right? From A to B.
Yes. No, not from
Okay.
A to B, V to V. So for example, here in this example which I have described, t is from R2 to R2.
Okay.
Okay. And beta and gamma are basis for R2.
Okay.
Fine.
Okay.
Two matrices are similar, then
Okay. So the next topic is affine subspaces and mapping. So let V be a vector space, and affine subspace of V is a subset L such that if you are able to express L as V plus U, where U is the subspace. Okay, note that this V is not unique, but the U is unique for a given affine space L. Okay, and what do you know about the dimension of L? Dimension of L is same as dimension of U. Okay. So, for example, you look at this graph here. In this graph, the red line, which one of this red, green, and blue? You have three lines. Which one of this is a subspace?
Red one.
Right. So this is a subspace. Right. And let's say this is your U. So what about this blue and green lines? They are
Affine subspace.
They are affine subspaces, because for affine subspaces, the visualization you know that they are lines parallel to this subspace. Okay, so any line parallel to this kind of a subspace is a affine space. So the same thing in three-dimensional, how do you visualize? Any plane parallel to a plane passing through the origin. So now this is a plane passing through origin. So this is a subspace and this is a parallel plane. So you know that this is an affine space. All right. Now how do you do addition and scalar multiplication on affine spaces? So if you have two vectors in affine space, you know that you can express as v plus u dash. This v is fixed. Only the elements of subspaces are changing. And you know how to do addition in subspaces. So you are again going to fix this v and then you are going to do the addition for the elements of subspaces alone. Same way for scalar multiplication, you fix the element v and do the scalar multiplication only for the element of u. Okay. So one thing before answering this question, I will tell you so that answering this question is easy. So for any subspace ax plus by plus cz, so if this is a subspace, the corresponding affine space, how it looks, is of the form ax plus by plus cz is equal to
b, some constant.
Right? So now can you answer this question? So you have L1 and L2 given here. Okay, these are affine spaces. What should be the corresponding W1 and W2, the subspaces for L1 and L2?
Option 3.
So x plus y plus 2z is equal to 0 for
Zero.
W1. Right? And for this 2x plus y plus 2z is equal to 0.
Zero.
2. Right?
Ma'am, in this case, we just check the equations only.
Yes. Just check the equations. Yes. Okay. Fine. Look at this now. You have an affine subspace L1 and L2. Now W1 and W2 are subspaces corresponding to L1 and L2. First of all, what is W1 from this? Can you tell me?
X plus y plus 2z equal to 0.
W1 is equal to x plus y plus 2z is equal to 0. What about W2?
Z equal to
0.
So you have now z is equal to 3. So now for W2, the parallel plane corresponding to z is equal to 3 is z is equal to
0.
Yeah. So you can represent it in this way, right?
Okay.
This is only z is equal to 0. It's correct only. Okay. Just representing it in this way. Now, what is the basis for W1? How can we find?
So x equal to y minus 2z.
Okay, first of all, let's see whether this statement is true. So we have to check whether these two are first of all here. So the first one, 1 comma minus 1 is of course an element here. What about 0 comma 1 comma 2?
No, ma'am, it's not there.
This does not belong to W1. So this
W1.
is incorrect. What about this? This is the XY plane. This is the XY plane. It means this is correct, right? Option 2.
Yeah, correct.
Yeah. Now what is
X comma y
W1?
comma 0.
Yeah. And what is W1 intersection W2? So you have Z is equal to 0 for W2. So when you substitute it here, then you have for W1 intersection W2, you have set of all x comma y comma z such that Z is equal to 0 and x plus y is equal to 0. So this means you have set of all x comma
Minus x comma
comma 0. So you can see that it represents a line passing through origin. One-dimensional space, right? So it represents a line passing through origin and it cannot be a plane. Okay, fine?
As the dimension is 1, so we are saying it's a line, right?
Yes.
Okay.
And the next topic is what is
Ma'am, sorry to interrupt you, ma'am. Can you just explain, ma'am, the option 3 only once again, ma'am?
Yes. So here this is x times of 1 comma minus 1 comma 0 where x is in R. So this means your W1 intersection W2 is spanned by this vector 1 comma minus 1 comma 0. And you know that span of any non-zero vector in R3 is a line passing through origin in R3. Okay?
Yeah, ma'am. How, ma'am? Just, ma'am, recapitulation. I just need, ma'am, how you get, ma'am, intersection of W1, W2, ma'am. Just, ma'am, because
I'm
W1 is
putting the conditions of both W1 and W2. So in W1 I have this condition and W2 I have this condition. So I'm putting both the conditions together. First I substitute Z is equal to 0 here. Okay. And then I have remaining x plus y equal to 0. And I also put the Z equal to 0 condition here. So I get only x plus y equal to 0. And now x plus y equal to 0 rewriting, I get y equal to minus x. So this entire set is reduced to x comma minus x comma 0.
Thank you, ma'am.
Okay.
Further division to 1 minus 1 0, right?
Yeah. So we are just replacing, just taking this x commonly. So you are having just the vector 1 minus 1 0. So this is a basis. Okay. So the next topic here is dot product. Dot product of two vectors, you know that it is u1 v1, u2 v2 plus etc. un vn. And what is norm of any vector? The length. The length of the vector is given by square root of.
That is square root.
Right? This is the norm. Right? And in fact, you can see that norm of a vector is equal to square root of u dot u. Right? And what is the formula for angle between two vectors? Cos inverse of u dot v by square root of u dot u into v dot v. Okay, so these are some formulas you need to remember. And what is inner product on a vector space? Inner product on a vector space is a function from v cross v to r which satisfies all these conditions. So the first one is the non-negativity. So inner product v comma v is positive for all v in non-zero, and it is 0 only when v is 0. And then you have linearity in the first variable, right? You have linearity in the first variable, and then so this is linearity. This is linearity, and then you have the symmetric property. You can replace the positions, and then the property of the scalar multiplication. You can take the scalar outside, right? And from these three, you can actually write inner product of u comma v plus w as inner product of u comma v plus inner product of u comma w. So you have bilinearity, linearity in the first as well as the second variable. Same way, you also have inner product of u comma cv is equal to c times of inner product of u comma v. Okay, so all these properties are there for inner product. And for norm, you have three properties. First one is a triangle inequality. And in the second one, when you take out a scalar from a norm, it always comes out as a positive value only. Okay, and norm is always positive for non-zero values, and it is 0 only for the 0 vector. Okay, and what is a norm induced by an inner product? Norm of V
Length.
is, yes,
It's a length.
yes. Can you hear me? What's your
Oh,
doubt?
yeah, it's a length actually.
Yeah, norm V is the length of the vector. Yes, correct. Okay, so norm V is the length of the vector, and it is nothing but square root of inner product of V comma V. Okay, so when do we say two vectors are orthogonal? So two vectors are orthogonal when the angle between them is 90 degree. So this is for the dot product. So in general, for inner product u comma v is equal to 0. Okay, and a set of vectors, you call it to be orthogonal if inner product vi comma vj equal to 0 whenever you have I and j not equal. For different vi vj, the inner product should be 0. So then that set is called an orthogonal set. Okay, and always orthogonality implies independence, right? Because if the directions are different, you know that the vectors are linearly independent. And here, in fact, they are at 90 degrees. So you know that they are linearly independent, right? So orthogonality implies independence. And what is an orthogonal basis? A basis which is also an orthogonal set. That is an orthogonal basis. Okay. And how do you normalize a vector? Let us say you have, for example, 1 comma 1. How do you normalize this vector? Can you tell? Let v is equal to 1 comma 1. How do you normalize this vector?
Divide by its norm.
Yes. The standard inner product, the norm is square root of 1 square plus 1 square. So square root of 2. So the normalized vector is v by norm v, which is 1 by root 2, 1 comma 1. So orthonormal set also is just same thing only we have to do. Suppose you have an orthogonal set, you simply divide each of the vector by its norm. So that now what is the norm of this new vector? Norm u is equal to 1. Right? So in an orthonormal set, the vectors are orthogonal, and in addition to that, the norm of each vector is 1. So if you have an orthogonal set, you can easily convert it to an orthonormal set. Okay, and now orthonormal basis is a basis which consists of orthonormal vectors. Okay, so here each vector has norm 1. Okay, and orthonormal basis is a maximal orthonormal set. Okay, so if you add any element to that set, it cannot be orthonormal. And how do you apply? So this is the procedure I just told you. If you have a set of vectors which are orthogonal, find the norm of each of the vector and divide by the norms. Then you will get an orthonormal set. Okay. So choose the correct statement here. In an orthogonal set, the norm of all the vectors are equal.
No, false.
Norms
True only when you have an orthogonal set.
cannot be.
Yeah. In an orthogonal set, the vectors are linearly independent.
True.
Yes, orthogonality implies independence. In an orthogonal set, the vectors are linearly dependent. Definitely incorrect. If the columns of an n by n coefficient matrix A comprises the individual vectors of an orthogonal set in Rn, then there must be a unique solution to the system Ax is equal to B. Is that true?
Yeah.
Because orthogonality implies linear independence.
Yes.
Linear independence implies that rank of A is equal to n. And if rank of A is equal to n, you know it is a full rank matrix. So you have A inverse exist. So A inverse exists and you have a unique solution. Right? So this is the opposite. There are no solutions. So this is incorrect. The determinant of a square matrix formed by set of orthogonal vectors in Rn is non-zero. It cannot be 0. So this is incorrect because just what we saw. Orthogonality implies linear independence. So you have full rank matrix. So determinant is non-zero. Okay. So a set of n vectors can never form an orthogonal basis in Rn minus 1. Yes, because for Rn minus 1, any basis should contain maximum n minus 1 vector. Exactly n minus 1 vector in fact. Right. So this is incorrect. Okay. Fine. So what are the key points regarding orthogonality? Orthogonality implies linear independence. And if a matrix A has columns orthogonal, then what are the things you know about this matrix? Determinant of A is
Not zero.
0. And then you also know that Ax is equal to B has a solution, right? So because determinant of A non-zero, only this property also comes. Okay. So these are some important things you should know.
So, ma'am, then the last option would be correct, na, ma'am?
Which option?
The last option.
This one.
Yeah, it says it can never form orthogonal.
Oh yeah. I thought it can have, so I chose it to be wrong. It can never have. Yes, correct. Okay. Thank you for pointing. Okay. So what are projections? So the formula, this is the formula you need to remember. So this is the formula for projection of B onto A. So if you have two vectors, projection of B onto A, this is the formula. Okay. And same way, to find the projection of a vector onto a subspace, you need to have an orthonormal basis. Okay, you need to have an orthonormal basis. This is the first thing you need. So once you have an orthonormal basis, the next step is you have this formula for projection. Projection of V onto the subspace W is given by summation I is equal to 1 to n inner product V comma Vi into Vi. Okay. So here remember they are orthonormal. So each of them are having norm 1. Okay. So these two are very important formula when it comes to projections. Okay. So here you can choose any orthonormal basis. This orthonormal basis is not fixed. You can choose any orthonormal basis for a given subspace. Okay. Fine. So now when you consider projection as a linear transformation, there are some very important things which you should know. Suppose T of V is equal to the projection of V onto a subspace W. Okay. Now for this transformation T, so let's see a very simple exercise or example. So let's say T from V to V. Okay. So maybe let's say R2 to R2. It's easy to visualize, right? So that you can easily remember the answers without just remembering it. Okay, you can easily look at this example and tell the answers. Now let's say you are projecting vectors onto x-axis. So what happens when you are projecting vectors onto x-axis? T of x comma y is equal to
x comma 0.
X comma 0, right? So what is the range of T? The range of T is set up for x comma 0, right? So what is the range of T?
1.
Range. All the vectors x comma 0, right?
Okay, yes. 1 comma, okay. 1, yeah.
No. What is the range again? What is this set? What is this set?
X-axis.
Yeah, so this is your x-axis. So this
from
is
1
your,
to infinity?
No, this is your entire x-axis, minus infinity to infinity, the entire x-axis. So here the range of T is nothing but W. Okay. Now what about the rank of T? What is the dimension of the range?
1.
Okay. So it is actually the dimension of W, right?
Yes.
Rank of T is nothing but the dimension of W. Right? In this case, it is 1. And what about the kernel T? What is the kernel here? See, for kernel, you just have to look at the perpendicular space. So this is your x-axis. So your y-axis is the perpendicular line to x-axis. So that will give you the kernel. Can you quickly verify? Take any element from the y-axis. It is 0, 0, right?
Yes, ma'am.
Yes.
Right. So what is this y-axis representing? It is your orthogonal complement of x-axis. So kernel of T is your orthogonal complement of W. Okay. So this is an example from which you can easily answer this question. If you are not able to remember the answer, you can quickly go to this example and verify. Okay. So orthogonal
Is this accordingly to all that answers to this? Like
yes.
for the
For
every
any
time the answer is same?
yes, for any transformation V to V where T is a projection of a vector onto a subspace W, range is W, rank is dimension of W, kernel is W per, the orthogonal complement. Okay, and what is the orthogonal complement? The set of all vectors in V where the inner product V comma W is 0 for all vectors in W. Okay, so this is the orthogonal complement, which is the kernel of T here. Okay. What are some very important things about the projection map again? So PW square equal to PW. So if you have a matrix which is representing a projection, then the matrix also should satisfy this property, that is A squared is equal to A. Okay. And always the projection of a vector cannot be longer than the vector itself. Just look at this image. So this is the original vector and this is the projected vector. You can obviously see that the projected vector's length is smaller than the original vector, right? So the projection vector is always smaller than the original vector, smaller than or equal to the original vector. Okay. Okay. So now you take two vectors v1 and v2. What is v perp can you find? Where v is the space spanned by v1 and v2. How will you find? This is the definition of orthogonal complement. How can you do? So let us take some vector x comma y comma z. Let's say it is orthogonal to 1 comma 1 comma 0. So what is it you will get? X plus
Y plus Z 0. Okay, X plus Z.
Right? And x comma y comma z dot product with 0 comma 1 comma 1 is 0. So what does that give you?
Y plus Z equal to 0.
Y plus z is equal to 0. Now from this what you can say, x is equal to minus y and z is equal to minus y. So what is your v per? It is the set of all
minus y comma y
minus y in R. So or you can say span of 1 comma minus 1 comma 1. Right? So you take any vector of this form, it is orthogonal to this as well as this, correct? Yeah?
Yes, ma'am.
Okay. Okay, now you have two subspaces W1 and W2.
I really don't understood the V perpendicular part.
We are looking at all vectors which are perpendicular to the space spanned by these two vectors. So you don't have to look at the entire space when you have the basis, you just have to look at the basis vectors. So you take a random vector from here, okay, and then we know that if you take any vector from V perp, it should satisfy the condition that it is orthogonal to V1 and V2. So the dot product with V1 is 0, the dot product with V2 is 0. So now the dot product gives me x plus y equal to 0 and y plus z is equal to 0, which reduces to x is equal to minus y, z is equal to minus y. From this, I know that any x, y, z will satisfy this condition. Okay, so here x, y, z is a random vector from my V perp. So any vector in this V perp satisfy this condition. So V perp is the span of 1 comma minus 1 comma 1. Now do you understand?
We can
Are you
also
writing opposite
minus
this
1 comma 1 comma minus 1, right?
See, it is the same only, right?
Okay.
You can write it if you want. You can
Okay.
write it like this also.
We can write either way. Okay, fine.
Fine. Okay, now you have two spaces W1 and W2. right? Now W1 is set of all x comma y such that y is equal to 2x, and W2 is set of all x comma y such that y is equal to minus 2x. Okay. Now let us say you have x comma y equal this space. What is the like you can take a basis and do the exact same process. Can you tell a basis vector here for W1? So if you put
1,
x is
2.
1, 2.
yeah, for W1 it is a span of 1, 2. So now if you are taking an x comma y in W1 perp, you will have x plus 2y is equal to 0. So it means what? You will have
X equal to minus 2.
2y is equal to minus x.
Yes.
Right? So which equation is satisfied? This one, right? Not this one. So this one is your W1 perp, correct?
Yes, ma'am.
Okay. And what about W2? What is the span of this set?
Minus 2, comma 1. Minus 1, comma 2.
1, comma minus 2, right? X is equal to 1 means y is equal to minus 2. Now, if you take any random element of W2 perp, then you know that x comma y dot product with 1 comma minus 2 is 0. So it means x plus 2y is equal to 0. Sorry, x minus
2y equals.
X minus 2y is equal to 0. So you have x is equal to 2y. So this is a correct option. Okay. Is it clear how we are finding the orthogonal complement? Is this part clear?
Yes, ma'am.
Okay. Fine. So this is something important about projections. Suppose beta is an orthogonal basis in an inner product space. If there exists some vector v such that inner product v comma vi equal to 0 for all I equal to 1 to n. Okay, it means we are considering a vector orthogonal to all vectors, all the basis vectors, then v is equal to 0. Is it true or not?
True.
Right? You can visualize it in many ways. One way is that, see, v is a vector in v and this is a basis, right? So this means that what? You know that v can be written as a linear combination of the vi's, right? Now what is inner product v comma vi? Let's say vj. You know that it is an orthogonal basis, right? So here you know that the coefficient is alpha j and this is equal to 0, right? So like this, each of the coefficient is 0. So this is true for all j. So each of the coefficient is 0. If each of the coefficient is 0, then you know that v is equal to 0, right? So you know that this is the correct option. There exists an orthonormal basis for Rn with the standard inner product. So for Rn, you know that what is orthonormal basis? This standard inner product is there. Standard basis is there, right?
Yes.
So you know this is correct. What about option 3? What is range of PW intersection null space of PW? First of all, what is range of PW? It should be W, right? Range of the projection is W and the kernel of the PW is W perp. What is W intersection W perp? Look at this image. This is your W.
Null.
This is W perp.
Oh, sorry, the origin. My mistake.
So the intersection is just the origin. Okay, so this statement is true. This matrix cannot represent a projection. Why? What is A square?
Has to be A.
Yeah. Is it equal to A? So check this, 1 minus 1 with this you get 1. 1 minus 1 with this you get minus 1 minus 1 minus 2. So you see there, this is not equal to A, right?
Yes.
So you don't even have to compute this. From this itself already know it is not equal to A. Right? So this cannot represent a projection, so it's correct. Okay? We have just used the properties of projection and orthogonal properties. Is this clear, this question? Yeah. Okay. Consider V equal to R3 with inner product, the dot product, and you have W where X is equal to Y and Z is equal to 0. Okay. Now PW is a projection on W. First of all, let's decode W. W is the set of all X, Y, Z such that X is equal to Y. So you have X, X and Z is 0. So this is your space. Right. Now this is nothing but span of, can you tell which vector?
110. 110.
Okay. So now quickly tell me what is the dimension of W?
1.
1.
Right. Dimension of W is 1. Now what is the dimension of image space of PW? They are asking. What is the image of PW first of all? Is W.
W. Yeah.
Right. So the dimension of image of PW is then?
The image of W. 1. Dimension
1.
of image. Yeah.
And what is the null space of PW? It is W perp. Okay, one important property again here is, suppose you have a vector space V and W is a subspace of V. Then dimension of W plus dimension of W perp is equal to dimension of V. Okay, this is because PW is from V to V, right? And when you apply the rank-nullity theorem for PW, this corresponds to rank of PW and this corresponds to nullity of
Null space.
PW. Okay, and hence you have this property. So from this property, you know that dimension of W perp is 2. Okay, now V belongs to W. Okay, this is another important property. So let's just look here itself, this example. What is T of X comma 0? Take any element from x-axis. Now what is T of X comma 0? Under this map.
X comma 0.
X comma 0 only, right?
Yes.
So it means what? So any element from the subspace itself is mapped to the same vector. So if V belongs to W, then maybe I'll write it in red because it's an important property here. So if V belongs to W, then PW of V is equal to V. Okay. So now with this, can you tell what is norm of PW of V? It should be same as norm of
V.
3. Yeah.
which is again 3. Okay, fine. What about the last question? Let A be the matrix representation of PW with respect to some orthonormal basis, beta and gamma for V and W respectively. Find the dimension of the null space of A square. What do you know about A square?
It is equal to A.
Yes, A square is equal to A, right? And what do you know about the null space of A? What do you know about the null space of W perp, right? So you already know the dimension of W perp. What is the dimension of W perp?
2.
2. So the answer is 2 here. Do you understand?
Okay.
Yeah. Null of A square is equal to null of A, which is
Dimension of W perp.
Yeah. So it is 2. Okay. Fine. So the Gram-Schmidt orthogonalization, you just have to remember this formula. There is nothing more to explain in this revision session. You have to use this formula. If you want some examples, please go to the live session video and check it. And also it satisfies this particular property. Okay. So you know that if you are given with this set of vectors, then the span of that particular set of vectors is same as the span of the final set of vectors which you are getting. Okay.
Ma'am,
Fine.
and one more thing, ma'am. Like for this, say for example, if a set of vectors is given, so we'll have to check, like, if they are orthogonal or not, right? Basically, this is must, right, for this thing.
Yeah, you can do that. So usually when you are asked to apply Gram-Schmidt, they don't give an orthogonal set, but yeah, you can check it if you want.
Okay.
Okay, fine. So this formula you need to remember, and you already know that any finite dimensional space, inner product space, has an orthonormal basis. Okay. So what are orthogonal transformations? Orthogonal transformations are linear transformation which satisfies this property. That is, inner product TV comma TW is equal to inner product V comma W. What happens if these properties are there? If this property is there, then you know that norm of TV is same as norm of V. Okay, and angle between V and W is same as angle between TV and TW. Okay, so for orthogonal transformation, these are the very important properties. And what about the matrix of an orthogonal transformation? The matrix of an orthogonal transformation is called an orthogonal matrix. Okay. Now, what does it satisfy? It satisfies this condition that A transpose is equal to A transpose A equal to I. So the matrix of a, let's say you consider the standard basis or any orthonormal basis. Okay, then the matrix which you obtain is satisfying this condition. Okay, and the other thing is that what does this imply when you consider the rows or columns of the matrix? The rows of the matrix are orthonormal and the columns are also orthonormal. So only when both the rows as well as the columns are orthonormal, the matrix is orthogonal. Otherwise, only if one condition is satisfied, it cannot be orthogonal. Okay, both these conditions are required. So regarding orthogonal transformation, you know that the norms are preserved, you know that the angles are preserved, and the matrix representation satisfies this property so that the rows and columns are orthonormal. Okay, and what is the, yeah, here exactly the same thing is given in this question. So if you have a 3 by 3 orthogonal matrix, what do you know? The rows are orthonormal. So if the rows are orthonormal, you know that it forms a basis for R3. Okay, the columns of A form an orthogonal set of vectors in the inner product space R3 with respect to the dot product. We saw that the rows and columns both are orthogonal, so both are correct, right? What should be the rank of A? Can you tell?
3.
Yes. So this is incorrect. And always, since the rank is 3, Ax is equal to B will have a
Unique solution.
unique solution. So this is also incorrect. Okay, fine. One thing which is not given here, what is the determinant of an orthogonal matrix?
Non-zero. Non-zero.
More than that? You have A transpose is equal to identity, or A transpose actually and.
A transpose equal to A inverse.
Okay, 1 determinant.
Determinant is 1.
So you have determinant of A square is equal to determinant. So determinant, let's maybe write it that
A
way.
into A transpose.
Determinant of A transpose is nothing but determinant of A into determinant of A transpose, which is same as determinant of
Determinant of A is plus or minus 1.
square, which is equal to 1, because determinant of identity is 1. Right? So this implies that determinant of A is
Plus minus 1.
plus or minus 1. Okay, this is a important property about the determinant of an orthogonal matrix. Is that clear? Yeah. Oh, Okay. I hope this session was useful for everyone. Tomorrow I am floating a Google form. So you can mention whatever doubts you have from the entire syllabus in that Google form, so that that doubts can be discussed in the next TA session. Okay. So with this, shall we wind up the session today?
Okay, ma'am. Thank you.
Thank you, ma'am.
Thank you. Any questions? Yeah.
Ma'am, I'm finding a bit difficulty with affine transformation.
Sorry, I cannot understand.
I'm finding some difficulty with affine transformations.
See, I have tried to cover most of the important topics required. If you have some more questions apart from that, please refer to the live session videos. You want affine transformations to be explained, right? That is your question, if I'm correct, right? So please refer to the live session video. Fine. Okay.
Ma'am, I have a small question.
Yes.
Might it will be silly. In there will be any weightage given to the